So this is Math 150, Section 2. We'll say Lecture 36, the last lecture. Whatever you guys want to talk about. Preferably math related, preferably Calc 3, but... Yes? I'm sorry? Jacobian. Okay, so for us, I'm not going to ask you to calculate a new Jacobian for the exam. The Jacobian is the change of variable formula. It tells you the exchange rate to go from dx dy to maybe du dv. Or if you have three variables, dx, y, dz, to something else. So the big ones you need to know are polar. Dx dy goes to r dr d theta. Cylindrical, dx dy dz goes to r dr d theta dz, and z is basically just along for the ride. And then spherical, dx dy dz goes to rho squared sine of phi d rho d phi d theta. It doesn't really matter what order you write the d rho d theta d phi, as long as you have the bounds correspondingly correct. Now what's nice is, what does a sphere look like in spherical coordinates? A box. And so you can often reorder the integration very easily because you don't have bounds of integration depending on bounds of integration. If I give you, a shape like this, I have, x goes from maybe 0 to 1. Here's y1 of x. Here's y2 of x. Y goes from y1 of x to y2 of x. If I want to switch the orders of integration, this is a little bit painful. I then have to figure out what's now x1 of y, what's x2 of y. If instead I have x goes from a to b, y goes from c to d, I'm integrating over a rectangle. I can switch the orders of integration if the integral of the absolute value is finite. That's Fubini's theorem. And then I don't have to worry about how does the region of integration, how does the bounds of integration change. So what's nice about spherical is that with spherical, we're integrating over a box. And so the bounds of integration don't depend on the other variables. So if people want, we can do a spherical integral, we can do a polar integral, we can move on to something else. Yes?
Can we see the spherical?
Sure. So let's do people want me to do the same one as in 9 a.m. or a slightly different one? Same one? All right, same one. They'll minimize the chance I get it wrong. All right, so let's consider the integral over a sphere of radius r, e to the negative x squared, I think it is positive, y squared plus z squared times the square root of x squared plus y squared plus z squared dx, dy, dz. Okay. By now, we've been together for almost a semester, like a few hours away from that. You should realize that I like to give you sometimes more information than you need for problems. I sometimes like to do things to trick you. But if it's on an exam, it's got to be a problem you can do. There's got to be a way to look at it so the algebra and the calculus is not that bad. So if I'm giving you a problem like this, things are probably chosen so that if you look at it the right way, it is going to be doable. Looking at it in Cartesian coordinates is not that way. Right? This is screaming at you spherical coordinates. And what's nice about this is it only depends on the sum of the squares of x, y, and z. And so because it only depends on the sum of the squares, I don't really have to remember, now what is x, now what is y, now what is z. If I gave you e to the x, then that would be a lot harder, because then I would have to remember that stuff. So I would have to remember x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. Right? You need to know this, and you need to know dx, dy, dz goes to rho squared d rho d phi d theta. And you need to know rho goes from 0 to r, phi goes from 0 to pi, and theta goes from 0 to 2 pi. Yes?
What about the sine?
Yeah, that would be a really good thing to include. Thank you. And so I would be in real trouble. So rho squared sine of phi d rho d phi d theta. Thank you. Yes? I'm sorry?
How many points on an exam would you take after that?
Depends on how well I've been doing. Depends on what mood I'm in. You know, did the Red Sox beat the Yankees? Did they lose? A lot of it is, are you clear? And so it also depends on how does it change the problem. So for instance, if you change a problem to make it of almost equal difficulty, then it's worth only a small ding. If by making an algebra mistake like this, all of a sudden you take a very difficult integral and now you make it much easier, then that would be worth a lot more. So some of it would become a function. It would probably make, for this, the actual integration would not be that much worse for this problem with a sine phi or not. So it would probably be on the order of 1 or 2 points to just lose that. But I don't want to have to figure that out for any of you. So do better than I do. All right. So now we want to convert this to polar. I'm sorry, to spherical.
Well,
yes?
don't you just also put what rho is?
I'm sorry?
You can define rho.
Right. And so for here we would have rho squared is x squared plus y squared plus z squared. So we're very fortunate for this problem that it doesn't depend on x, y, or z independently. It only depends on them bundled together like this. So let's just do this, really slowly. We now get our integral is, we'll have e to the rho squared squared, which is rho to the 4th. Then what's the square root of x squared plus y squared plus z squared? Right, the square root of x squared plus y squared plus z squared. Rho. So it'll just be rho. So my function just becomes e rho to the 4th times rho. Now I put in the measure, which will be rho squared sine of phi d rho d phi d theta. So since I'm doing it in this order, theta goes from 0 to 2 pi, it's outside. Next is phi goes from 0 to pi, and then rho goes from 0 to r. You can probably guess now why I put in a square root of x squared plus y squared plus z squared. I'm trying to make the integration nice. All right. Now, the first thing to note is all of my rho dependence is here, all of my phi dependence is here, my theta dependence is just 1. I don't have something like the cosine of rho theta, where I have the rhos and the thetas mixed up. I can split this as 3 calc 1, 2 integrals. This is just the integral theta goes from 0 to 2 pi of d theta. The integral phi goes from 0 to pi of sine of phi d phi. And then the integral rho goes from 0 to r of e rho to the 4th rho cubed d rho. Okay? So now, let's do the integration. And this is the advantage of doing spherical coordinates for this problem. It's a box. The bounds of integration don't depend on each other. I can split it like this. What's the integral theta goes from 0 to 2 pi of d theta? I'm sorry? Theta. Okay, so the integral is theta, then I evaluated 0 and 2 pi, and we'll just get a 2 pi there. The next one is, what function has derivative sine of phi? So it's negative cosine phi at 0 and pi, and then we'll leave our rho integral. 0 to r e to the rho to the 4th, rho cubed d rho. So the first one here is just going to be a 2 pi. The next one, when I put in pi, I get negative cosine of pi. Well, cosine of pi is negative 1, so I get a 1. Then I subtract off negative cosine of 0. So I'm subtracting off negative 1. So I get 2. And then I have that rho integral. So let's just do that rho integral slowly. This is just a calc 2 integral. we need the integral rho goes from 0 to r e to the rho to the 4th rho cubed d rho. So what technique should we use for this? U substitution. There are two good choices for U substitution. There may be others, but there are two ones that are naturally good. Can somebody give me one of the good choices? Rho to the 4th. That's the one I would do. There is another one you could do. E to the rho to the 4th. Either one would work. I prefer rho to the 4th. I think it just makes things a little bit simpler for me, but either one is fine. So go slowly. Don't try to skip steps. I am not allowed to use my mind reading skills when you are doing your exam. Okay? I have to grade you based on what is on the exam. I have been doing multivariable calculus longer than probably everybody in this room has been alive. Right? I've been doing this for a long time. When I see incomplete fragments, I have a pretty good idea of what you were trying to do. But I have to grade you on what is there, because there are multiple ways to get certain quantities. So take the time, write down clearly what you're doing and why. You had 50 minutes on the second exam to do 4 problems. You have 2.5 hours to do 7 problems for the final. So you have a lot more time per problem. Okay? So part of the purpose of the second exam was to give you a sense of where your timing is. You should be able to do 4 problems in 50 minutes. But there will be enough time on the final so you will not be stressed or pressured as much. Go slowly, show me what you're doing. You're also less likely to make a mistake if you do it this way. So if u equals rho to the 4th, du is going to be 4 rho cubed d rho. I can solve for rho cubed d rho because that's what I have, and that's just going to be 1/4 du. And then rho goes from 0 to r, so u is going to go from 0 to r to the 4th. And now that I have everything here, it makes the substituting a lot easier. So my integral is going to be the integral u goes from 0 to r to the 4th, e to the u, 1/4 du. All right, so that's just going to be 1/4 e to the u at 0 and r to the 4th. So that's just 1/4 e r to the 4th minus 1/4. And I would just substitute that in. Okay? So any questions on how we would do this problem? Yes?
Where you change
Rho?
cube, you go 1/4 du.
Well, so I'm substituting. I mean, what I could do is I could substitute for d rho. And so let me show you a longer, painful way to do this problem. All right. So I want to make sure that everybody's comfortable with this part, and then I'll show you just a longer way. A lot of life is finding good ways through algebra. Yes?
The integral e to the u.
Right? What function has derivative e to the u? That's just e to the u.
But don't you also divide it by the derivative of u? Or does it not matter? That's the u. The derivative of u is 1.
Well, if I give you e to the u squared, its derivative would be e to the u squared times 2u.
Okay.
And so when I want to integrate this, I need e to the u times 1. And so everything is fine. If you want over here, if I have e to the rho to the 4th, I really need a 4 rho cubed. Instead of doing u substitution, I could put a 4 here and a 1/4 there, and essentially just skip the u substitution. If you're really comfortable with calculus, you can do that. If you're not as comfortable, take the extra time, write a few more steps. Any other questions on this before I show you the longer way to do the u substitution? Okay. So this will go to your question. I wrote it as rho cubed d rho because I know that I have a rho cubed d rho. And I'm just trying to solve for that. So what if I didn't see that? So here's a longer way of doing the problem. So I have the integral rho goes from 0 to r, e to the rho to the 4th, rho cubed d rho. So I'm going to let u equal rho to the fourth. So rho goes from 0 to r, implies u goes from 0 to r to the fourth. du is 4 rho cubed d rho. So d rho is 1 over 4 rho cubed du. I just brought it over. Now, I'm going to do it really long and really painful. I should not do anything here because this rho cubed is going to cancel with that rho cubed. But I can't have rho on this side. It's got to only be in terms of u. So I've got to replace rho with u. Well, if u equals rho to the fourth, that means rho equals u to the 1/4, or rho cubed equals u to the 3/4. So I could then write this as d rho is 1 over 4 u to the 3/4 du. And then my integral would become, the integral u goes from 0 to r to the 4th. E to the rho to the 4th would become e to the u. Rho cubed would become u to the 3/4. And then d rho would become 1 over 4 u to the 3/4 du. And you would see now that those cancel. And so this is a little bit longer way to do the problem. You will get the same answer. You'll just do a little bit more algebra along the way. And so if you didn't see that, you could do it this way. But the nice thing is I've got a rho cubed d rho. If I can somehow solve for rho cubed d rho, that's going to be much nicer. And so I don't need to solve for d rho. I need to solve for rho cubed d rho. And that's what we were doing over here. We solved for rho cubed d rho. Okay. Other questions on spherical integration, stuff like this? Yes?
Can you explain how to go over picking your boundaries for integration?
Sure. So if we're doing something that looks like it's a yes.
Just like you went from 0 to r to the 4th.
I'm sorry?
No, you went from 0 r to the 4th. Why did you switch from 0 to 4 to 0 to r to the 4th?
Well, see, u is rho to the 4th. Rho goes from 0 to r. So since u is rho to the 4th, 0 to the 4th is 0, r to the 4th is r to the 4th. So I like to be extremely pedantic and just put in every single step. And then when I put every single step in here, now when I need to substitute, all my information is here and I can just quickly look at it. What should my bounds of integration be? It is almost surely something like this where the mistakes happen. Okay.
Was going from 0 to 1 and b then?
I'm sorry?
If the bounds was because normally we put...
Well, if it's a sphere of radius 1, then 1 to the 4th is still 1. And so this is one of the dangers when you sometimes work with a unit sphere, is you don't necessarily see how things are changing. And that's one of the reasons why I want to do r to the 4th, to just really see how that's coming into play. Okay, so the question was, how do you find the boundaries for integration? So for instance, here is y is x to the 4th. Here is y equals x cubed. And so I need to know enough to be able to plot them and see which one is above the other. X cubed is going to be greater than x to the 4th from 0 to 1. And they're both going to be equal at 0, they'll both be 0, at 1 they'll both be 1, and then in between it's going to look something like this. So is this region vertically simple? Once I enter, do I stay in and then do I leave? And never to return. Yep, vertically simple. Enter, stay in, leave, never to return. Is it horizontally simple? Yeah. So I can integrate it either way. It all comes down to which way is going to be better. So for the double integral, do we want to do this horizontally then vertically, or vertically then horizontally? What do we want to do for this problem? I'm sorry? I can't hear you.
Horizontal.
Why horizontal?
It's easier to see which one is greater.
Okay. So we have one vote for horizontal.
Just do vertical because we already have the equations.
I have one vote for vertical. What function are we integrating? I don't. This is being recorded. I can go back and check. I don't think I ever told you what function we're integrating. I did not. Right? Yeah, it's like this call is being recorded for your, for your. If there's time after class, I will tell about the phone call that I got with my two kids, where the person said, it's been so difficult trying to reach you. You're harder to reach than my husband to get him to make dinner. And I asked, when did you try to call us before? And it turns out they had never tried to call us before, and they were trying to lie and imply that we had already talked to them, and they were trying to return our previous conversation. Got all the way up to the manager's manager on this one. I never mentioned what we're integrating. That's how you choose which way you want to do the integration. It's what makes the integration easier. Until I give you the function, it's not clear if you want to do it vertically or horizontally. So let's just set it up both ways. So here, this is my bottom curve. y1 of x is x to the 4th, and this is y2 of x is x cubed. So I could do this as the integral x goes from 0 to 1, the integral y goes from x to the 4th to x cubed, f of xy dy dx. Right? Now I need to try to do it the other way. So if I want to do it the other way, this is now the boundary curve. This is going to be my x1 of y, and this will be my x2. So I'll redraw it. So if this is y equals x to the 4th, I want to write this as x as a function of y. How would I write that as a function of y? If y equals x to the 4th, so x is y to the 1/4. So my upper bound, x2 of y, is just y to the 1/4. Over here on this side, I have x would just be y to the 1/3. So I would get x1 of y, my starting value, is just y to the 1/3. So if I do it this way, I would get the integral y goes from 0 to 1, integral x goes from y to the 1/3 to y to the 1/4, f of xy dx dy. And as long as the integral of the absolute value is finite, I can switch the orders. If the regions are finite, as long as your function is continuous, this will be the case. And now, to choose which one is better, I need to see what the integral is. Question?
Why is it y to the 1/3 and then y to the 1/4?
Because I'm starting here and ending here.
Okay.
So this is the first one.
Yeah.
So when your number is large, which is going to make your number smaller, taking a third root or taking a fourth root? Which is going to be smaller, the third root or the fourth root? Let's take 2 to the 12th. What's the cube root of 2 to the 12th? 2 to the 4th. What's the fourth root of 2 to the 12th? 2 to the 3rd. So for large numbers, the cube root is going to be larger than the fourth root. But for small numbers, it goes the other way. Because as you take a square root, what's the square root of 1/4? When you take the square root, when you take these roots, it makes your number climb up towards 1. And so the third root is going to be less than the fourth root. And so now we would have two different integrals. Which integral is better? Depends entirely on the function I give you. What happens if you try it and it's not working out well? Try the other one. What happens if that's not working out?
Go back to it.
Go back to the first one and say, maybe is there some other coordinate system I can do? Can I change it? And if that's still not working, you've made an algebra mistake. Because I'm not going to give you something that doesn't work out nicely.
So in the top one, I know that x goes from 0 to 1, but in the bottom one, how do you figure out that y?
Well, when x is 1, what is the value of y?
It's constant 1.
It's going to be 1. So this point here is 0, 0. This point here is 1, 1. You have to do a little bit of algebra to draw the picture. And so x goes from 0 to 1, y goes from 0 to 1. And so I can view this like that. So it lives inside the unit square. Okay, so just so you know what's in the 9 o'clock video in case you want to watch that and do other things here. We did do a Lagrange multiplier. We talked about level sets. I don't know if people want to do sequences in series. Yes?
It's just like a general question, but could you go over like the main topics that we should study, or you would recommend we study?
So I will send a review sheet that I've made that just highlights all the stuff we've done for the semester. And so it's got, here's the key points. You've also got the bulleted list of what was the key things in each section.
Okay.
When we're evaluating sequences of series, we want to use comparison tests. Are
Yep.
we free to use everything we evaluated in class?
Absolutely. And just write, we showed in class or we showed in the book that the following converges or the following diverges. You do not need to reprove that the harmonic series diverges unless I ask you prove the harmonic series diverges. But if you're trying to show that something diverges, so as an example, let's say I give you the sum and it goes from 1 to infinity of 1 over 2n plus 1. Does this converge or diverge? So what would you compare this to? I'm sorry?
1 over n.
Okay.
Yeah, harmonic series.
But 1 over n is greater than it.
1 over 4.
Great. Excellent. So 1 over 2n plus 1 is greater than or equal to 1 over 4n if n is greater than or equal to 1. And this is just 1/4 of the harmonic series. So if the harmonic series diverges, 1/4 of the harmonic series diverges. Right? So if you want to prove this rigorously, claim 1 over 2n plus 1 is greater than or equal to 1 over 4n. So this is the same as 4n is greater than or equal to 2n plus 1, which is the same as 2n is greater than or equal to 1. It's the same as n is greater than or equal to 1/2. So if this is true, this is equivalent to this statement, this is equivalent to this statement, this is equivalent to this statement. Since n is at least 1, we know 1 over 2n plus 1 is greater than or equal to 1 over 4n. And now what you can say is, this is going to be greater than or equal to 1/4 the sum n goes from 1 to infinity of 1 over n. And now you can use the comparison with the harmonic series. Yes?
For the convergence test, is there a rough order of which ones we should use first?
My first thought is always to do the comparison test. It's like if I give you a quadratic and ask you to factor it, is your go-to the quadratic formula?
Nope.
No. Right? That's your emergency strategic reserve. If all else fails, I will do the negative b plus or minus square root of b squared minus 4ac all over 2a. There is a formula for the cubic. There is a formula for the quartic, but not for anything higher. So if you give me a cubic or a quartic, worst case scenario, I could do something like that. But my go-to is to just look and see, can I see the factors? So I would say my first thing is if I give you a sequence, and then I want to know, does the series, does the sum of the terms converge or diverge? My first thought would be to look at this and see, can I compare this to something I know? And if that fails, then it's like, okay, maybe integral test, if when I convert n to x, it looks like something that would be easy to integrate, but I need the sequence to be decreasing or increasing. Then I would do, oh god, now I'm down to either root or ratio. Ratio is often a little bit easier to do than roots, and so I would probably try ratio before root. This is essentially the baby is crying method of mathematics. The baby is crying and you don't know why. You go through, does the baby want to be held? Does the baby need to be burped? Does the baby want to watch the Red Sox? You go through your list of things. One of them worked very well for Cam.
And so, for both the ratio and root test, if P is greater than 1, it converges, right?
No.
I mean, or is it less?
So we let rho be the limit as n goes to infinity of an plus 1 over an. If rho exists, then if rho is greater than 1, it diverges, less than 1, it converges, equals 1, no information.
And that's for both.
And that's for both. This is the ratio test here. The root test would be rho equals the limit as n goes to infinity of the absolute value of an to the 1 over n. And what's nice is it's the same condition on rho. The reason it's the same condition is it's essentially the same test. What is lurking in the background with the ratio test and the root test? It's comparison. The whole point about the ratio and the root test is you're basically a gold member and it will choose the correct geometric series to compare it to for you. It's just comparing it with a geometric series. But it knows what geometric series to compare it to. That's the advantage of using the ratio and the root test. And it's a way to try to make the algebra a little bit more automatic. Okay. Any other questions? People want to do any problems on these? People want to do a sequence series problem? Do you want to do a ratio test or a root test? Or
Yeah, let's do one.
let's do one. Good. All right. Let's let an be n to the n over 2018 factorial to the n. It's a fun problem. What can you tell me about 2018 factorial?
Finite.
I'm sorry?
It's finite.
It's finite. It's a fixed finite number. Does that have any n dependence? No, it's just a number. It's meant to try to make you scared. Make you maybe think, maybe I need to calculate 2018 factorial. It's just a finite number. Do you want to do ratio test or root test?
Root test.
Root test. So if we do the root test, let's look at the limit as n goes to infinity of an to the 1 over n. Given that everything is raised to the nth power, really good choice to do the root test. This is screaming. Were you just physically assaulted in class? Okay, we can talk. Unfortunately, I don't have the video evidence on this. So this is the limit as n goes to infinity of n to the n over 2018 factorial to the n to the 1 over n. And so this is just going to be the limit as n goes to infinity of n over 2018 factorial. And what is that limit? Infinity. So does this converge or diverge if I look at the sum? It diverges. It violently diverges. So while it was a good choice to look at the root test, there was a better test you could have done. Do you know what the better test is? Comparison with what? So you would have to give me a comparison with something that diverges. There's a better test. Yes?
Just look at the sequence diverges.
Yeah, the terms are going off to infinity.
Yeah.
Right?
Yeah, but that's infinity over infinity.
But once n is larger than 2018 factorial, the numerator is larger than the denominator. So imagine I give you an is n to the n over some number b to the n. If n is greater than or equal to b, then an is greater than or equal to 1. The terms are not going to 0. So there's no need to use the root test. Right? So if you want my go-to, what should I do first? Probably the first thing I do is just ask, do the terms go to 0? If the terms don't go to 0, there's no need to do anything more involved. Now, what if I gave you instead, Bn is 2018 factorial to the n divided by n to the n. And I wanted to look at the sum of the Bn's. Does that converge or diverge?
Is comparable to the harmonic series.
Well, I have 2018 factorial to the n divided by n to the n. Should that sum converge or diverge?
Oh,
Shouldn't it converge?
well, no, the sum of diverge.
So why would it converge?
Isn't it because the denominator is growing way faster?
The denominator is growing much, much faster. We actually just calculated that n to the n over 2018 factorial to the n, take the nth root of that, that goes to infinity. This is the reciprocal.
But isn't that just, once you do the root test, it comes out to be...
Well, so if we do the root test, what would be the limit as n goes to infinity of bn to the 1 over n? So it's the limit as n goes to infinity of 2018 factorial over n. And what's that limit going to be?
0.
So that's going to be 0. So I basically just took reciprocals. So if the original sequence converges to rho, the reciprocal converges to 1 over rho. So if the original one was going to infinity, this one is going to go to 0. All right. So what's nice is we actually did do slightly different problems here than in section 1. So you can actually get a little bit